So, to remember something here. This is the second reason I'm doing this, okay? Does anybody know what this is? If I write down this x squared plus y squared equals 4, do you guys know what that is, by any chance? What is that? Mm-mm. Thank you. This is known as a what? Equation of a what? Circle. Centered where? Good. At the origin with radius what? 2. You might say, is it really? Yeah, because the equation of a circle centered at the origin is of this form here, r squared, where that r value is positive. This is what we're talking about. You know, in this example, the radius, this is r squared here. Okay, and so you say is r squared 4, which means r is plus or minus 2, while your radius is actually what? 2. So this is kind of, you know, the general form for that equation, right? And so you might even look at Desmos and say, hey, does Desmos plot circles? And the answer is yes. Okay. Okay. So, okay, so here's your equation of the circle, ladies and gentlemen, right? And here is the graph of this thing. But I want to actually make a remark here. Okay? This is called a what? Formally, this is a, what is it? It's not a unit circle because the radius is 2. But what I'm looking for is this is known as a what? This is a relation. This is not a function. So you go, what do you mean? Well, if you look at this equation of the circle, this is in the family of curves known as relations. They're not functions. So you say, can I take the derivative this way? No, you can't. Because all these derivatives were given to you. This is a relation. This is not a function here. Right? They were given to you this way. You say, okay, y equals what? F of x, and you had to determine y prime. But you can't do that directly when you have a relation. And what other curves are under the relation? There's a lot of relations out there. You got hyperbolas, you got ellipses, you got, circles. In fact, there's a lot more curves out there that you can write as a relation, and you still need to find y prime, which is dy dx, right? So the question is going to be, when x squared plus y squared, when you're given a relation, how do you find y prime, which is dy dx? And that's where we're at. We're at the process known as, you're going to have to use implicit differentiation. This is, in my mind, This is really an application of what? Of chain rule. That's what this is. This is thought of as an application of chain rule to differentiate a relation, meaning finding dy dx. And the process is, well, I don't want to say it's a simple process, but there's a process, right? So here's what I'm going to say to you guys. Step one. Step one, take the derivative with respect to x of both sides. This is what they mean. This is use operator notation. So, a very simple kind of thing. So when I say derivative of both sides, you take d dx of the left, which will equal what? D dx of the what? Of the right. Okay? Maybe that's what you guys need to see. We're going to take the derivative of both sides. This is implicit differentiation. Okay. So now, ladies and gentlemen, you say, well, what does that mean? Well, what's the derivative of a sum? That's right. So we're going to differentiate the x squared plus this differentiate this what? Y squared, and that's going to be the derivative of a constant. Now, good. So pay attention to this detail now here. This is d dx, which means you're differentiating with respect to the what? X variable. Now, what I didn't say here is well, first of all, let's do this here. Can you guys tell me, what's this derivative of 2x by product rule? I'm sorry, I gave you the answer. Derivative of x squared. Told you I could do it in my sleep. The derivative of x squared is 2x, ladies and gentlemen. What's the derivative of any constant? 0. Now, here's where you really focus here. This is going to be interesting. All right? This is the part that's interesting. What I didn't say that you always have to assume, because it's actually true. I can prove it to you. You assume y is a function of x. You see that y variable? It's really a function in terms of x. You can think of it that way. That's the assumption. You see, I can go back and take this original equation and solve for y, and it's going to be in terms of x. Okay? And you get the top portion of the curve and the bottom, but I'm not going to go into that detail this morning. Now you say, how in the world can you differentiate y squared? Well, here's what today had to do with. Have you ever seen anything like this today? Triangle to the nth power, and that n, triangle to the n minus 1 times the derivative, that chain of the triangle. Have you ever seen that before? This is why I say you're really looking at what? Chain rule. That's 2y times dy dx, or y prime. This is by, again, what? Chain rule. Don't forget that. So an application of chain rule is implicit differentiation. You got to know chain rule if you're going to do implicit differentiation. Now, that means we have what? 2x plus 2y. I'm going to put times y prime, which is really dy dx. And that's going to equal what? 0. So you're really looking at all the gory detail here. 2x, 2y, y prime, 0. You're looking at what's left here. And I think earlier today we were using the gray. So let's just be consistent. Okay. Now here's the second part. That was step 1. Step 2. It's really a two-step process. You solve for what? Y prime. Y prime's right here by the chain rule. So how would you guys solve this for y prime? Right? Don't you subtract 2x from both sides? And now you have 2y times y prime becomes negative 2x, right? Don't you divide both sides now by what? By the 2y, right? Now what do you end up with? Right? Your 2's cancel, don't they? Yeah. So ladies and gentlemen, there is a way for you to find the derivative, dy dx. We just did. Yes, it's two variables. It's x and y. But ladies and gentlemen, you did your first implicit differentiation here. And you had to differentiate a what? A relation. Notice this. Didn't we say y is a function of x? Well, it doesn't matter. But so, ladies and gentlemen, this is where we're at. We're starting to talk about implicit what? Which is an application of chain rule. And of course, you might say, can I find locations of horizontal tangents? Sure. In this picture, you got a horizontal tangent where? Here. You got a horizontal tangent in this picture where? Here. Okay, so we can find horizontal tangent lines, those locations, meaning these addresses. And by the picture, what could you guys see? This is where x is 0, right? Y is negative 2. Here, this is where x is 0, y is 2. So graphically, I mean, I can find those horizontal tangents. But how did we do it before? Yeah, you set this what again? Derivative equal to 0. Solve for x. So that means, ladies and gentlemen, negative x over y equals 0. What does that mean? That means x is what? 0. Okay, so you can do the analysis. You find the location, find x is 0. You say, well, how do I get y? Well, isn't x squared plus y squared equal to what? 4. So if you plug in x is 0, isn't that 0 squared? What does that mean? That means y squared is 4, or y is plus or minus square root of 4, which gives you y is plus or minus what? 2. So this is the analysis, which is consistent with the picture. Horizontal tangents happen when x is 0, y is 2. When x is 0, y is negative 2. So this is the area where we're headed with some of these derivatives. Just so you guys know, with some of these relations, we can find those locations in the same way we did before. That's all. And I just wanted to share that with you, why you care about a derivative, and then the geometry of the picture, and this is implicit. So we're going to start that this week. So ladies and gentlemen, welcome back with chain rule, operator notation. As you guys can see, we used it here in implicit differentiation. That's the notation of choice. So we're going to continue tomorrow with implicit what? And when do you use it? Yesterday. When do you have a relation? Those of you guys who have taken pre-calculus. Anybody take that course? I don't want to ask. I don't want to know. Anybody take pre-calculus? When do you have a relation? Well, we'll see tomorrow. Okay, take care. Participation of today, implicit differentiation. I'm going to put that in our what? Let's put that in the comments section for folks here. Okay. And I have it even in the iPad for us this morning. Implicit differentiation. Now, what is this about? You might say, performing a what? Derivative on a, what's that word? On a relation. So if you go back to Math 260, okay, what you're looking at here is really a general form for the equation of a circle. Now, this is a relation. So how do we know it's a relation? Right? When you look at the graph, there's something called the what? This is the vertical line test. So vertical line test tells you that this is a relation, just so you guys know, okay? And if you actually draw a vertical line and you hit your curve at more than one spot, then you know that this is a what? Relation. So this is called the vertical line test. Okay. So we're talking about, again, relations. So all of these curves that we see here in this worksheet are relations. All right, you guys okay with that? Now, if you said to me, can we still find a derivative, dy dx? The answer is a big what? Yeah. Yes. However, we have to follow a process, okay? It's a two-step process. All right, you guys okay with that? You're going to differentiate both sides with respect to x. So you say, well, what does that look like? Well, here's what that looks like, okay? D dx of the left side, you go, what's on the left side? X squared plus y squared, okay, plus 6x minus 4y equals d dx of 15. Okay, this is step one. You differentiate both sides with respect to x. And you're using operator notation. Okay, so on the left side, I'm just going to use operator notation here. We have d dx of x squared, d dx of what? Y squared, d dx of 6x, okay, minus d dx of 4y equals d dx of 15 here. Okay, apologize for how that looks, but I want to write every step here for you. Okay, you guys okay with that? Now, once you do this, what do you guys have to do? Differentiate. I want you guys to know here, there's a big assumption. Y is thought of as a function of x. Don't think of that as a constant. So if we differentiate here, well, we get to use what? Power rule. That's 2x. If I differentiate here with respect to x, well, that's 6. Is that true? If I differentiate a constant, that is 0. And then over here, I'm going to say pull out your constant, 4. And now I have dy dx there. Well, this is good. That's really what I'm looking for. Because dy dx is the derivative. That's y prime, okay? You guys okay with that? We're looking for that. What you're going to have to consider is right here. Okay? You're going to have to use, what did we use yesterday here? Do you guys remember? Chain rule. It's chain rule. Okay? Because y is a function of x. It's that chain rule. You go, what chain rule? Well, if we had it's right, the power rule, remember? right? Any power, it's a power rule here. Okay, so you say, well, what does that mean here? That means we have 2y times what? Y prime, which is dy dx. This is where students get what? Confused every time. But not you guys, because you guys have been working what? Very hard on all of that. But that's what you're using. It's general. You differentiate that, you know, variable y with respect to x, so that's your 2y times dy dx. So that's the first step. Now let me put all the details together. 2x plus 2y times y prime, okay, plus 6 minus 4y prime equals what? 0. Because that dy dx is y prime, ladies and gentlemen. Okay? So far, so good? Okay, that's your step 1. So who remembers from yesterday, what was step 2? You solve for y prime. And this is where what comes into play? Algebra what? Algebra comes into play, ladies and gentlemen. Solve for the y prime. That's algebra. Now, I'm gonna do the following here. Okay, so hopefully your algebra skills are pretty good. And notice what I'm doing. I'm gonna subtract 2x from both sides, subtract 6 from both sides. This is sometimes known as translating. If you move a term to the other side, just change the signs. So if it's positive on the left, it'll be negative on the right. Okay, you guys okay with that? And then you might say to me, well, how do I get my y prime here? Okay, well, factor out y prime. So now you're going to have 2y minus 4 times y prime will be negative 2x minus 6. How do I get y prime again? Divide both sides now by what? 2y minus 4. So you get now what? Y prime, which is negative 2x minus 6 over 2y minus 4. Now, in some sense, you are what? You're done. You might say, what do you mean I'm done? Yeah, you're done. But if you look in back of the book, you see the negative sign in the numerator? You can factor out a negative. Okay, and you can put it at the same level. Here's what I'm saying to you. Let me do this way. I can factor out a negative from the numerator. And then, ladies and gentlemen, I can put the negative sign at the same level as my what? Division sign. And so what you're seeing here, there's your answer. Okay, easy peasy lemon squeezy. All right, so ladies and gentlemen, there's your derivative here for this equation of a circle. It's really a relation, and now I can do all kinds of things with this. Okay, you might say, what can I do? I can ask you this question here. Now that you have the derivative, what value of x will you have a horizontal tangent? Okay. When will you have a horizontal tangent? Well, do you guys remember that? What does that even mean? That's where the first derivative equals 0. Because that's the slope of the line tangent to the curve, right? So you have to set the first derivative equal to 0, and then you solve for x. Now, what does that mean? That means negative 2x plus 6 over 2y minus 4 equals 0. So once they give you a derivative, ladies and gentlemen, they can ask you something like that. Okay? Now, I want to warn you guys, generally speaking, for any curve, whether it's a function or relation, they may not ask you where's the horizontal tangents because the algebra might be impossible to do. So they're always very carefully selected questions. So don't go and try to find horizontal tangents for every derivative you see in your life. You may not be able to do it at all. Okay, so these are specially chosen. Now, here's another thing I want to remind people of. When is a fraction? You have to use some algebra. When is a fraction ever equal to 0? If you have a fraction equals 0, then what does that mean? That means your numerator has to be 0. Yeah. Okay, you guys with me on that? So how does that help us here? Well, what that means is, since I have a fraction equal to 0, my numerator is what? 2x plus 6. And now that is equal to 0. Now, the algebra is nice here. My God, this is even pre-algebra. Yo, Mr. Judge, God knows some algebra. Yeah, that's pre-algebra. So, okay. Subtract 6. You get what? 2x is negative 6. Divide both sides by 2. What is your x now? X is negative what? 3 here. Okay? All right, you guys with me on that one? X is negative what? 3. So you actually answered the question. X is negative 3. So if I go back at the curve here, remember this. Where is negative 3 at here on this curve? Okay? I guess here's negative, let's see, 1, 2. I guess it's right here. All right, so at negative 3. See that point? At this location, there's your what? Horizontal tangent line, okay? But there's another location. So this curve has what? 2 points on it where you have a what? Horizontal tangent line. Okay, and that happens when x is what number? Negative 3. Good. Okay, you guys okay with that? Now, here's the deal. We answered the question. These values of x, you get what? Horizontal tangents. They didn't ask you, though, for the y coordinate. They didn't ask you for the location. Sometimes they do, sometimes they don't. But if you said to me, what if they ask us for the location, the point? Well, you got to plug in. This is the original curve. Negative 3 for what? For your x. So that gives you negative 3 squared for x plus y squared plus 6 times negative 3 minus 4y. And what does that equal? That equals 15. Bless you. So we get 9 plus what? Y squared minus 18 minus 4y should be equal to 15. And it looks like that'll be y squared minus 4y. It looks like minus 9 equals 15. And then y squared minus 4y. Subtract 15 from both sides, and what do you end up getting? Right? Is that going to be minus what? 24 equal to 0? Okay. Double check. Okay, is that true? Is our arithmetic okay? And then I'm going to ask you guys, is that factorable? Y squared minus 4y minus 24?
Yeah.
It is? What's that going to be? I'm going to go back and erase all this.
Can I take a picture of it?
Well,
I mean, like,
it's a little too late, but
it's okay. Like, just scroll down a little bit.
you got the video.
Yeah, I know. Thank you.
Okay. So is that factorable, ladies and gentlemen? Can you get the y values? I don't know. Is that factorable? I'm not so sure. Two numbers multiplied together is negative 24 when added is negative 4. Is that 6 and 4? Double check. That's 2. This is not what? This is not factorable. So that's okay if it's not factorable. Okay. What would you guys have to do in reality? Use the Big Daddy quadratic formula. But the good news is they didn't even ask you for what? They didn't even ask you for what? The what? The location, the points. They just asked you for the x value. I just want to point that out to you guys, okay? A little bit of detail. And then, just to kind of go over just some of the basics and the fundamentals of what we know about some of these derivatives, okay? All right, so they may even take a point on the curve I'm going to get rid of this. It's in your notes. They may even take a point on the curve. So I'm going to call that a note. I'm going to erase this because it's in the video. You said, oh, Mr. Judge, what if they took a point on the curve like a location here? I don't know where it is. I got to be careful. There may not be a nice point I can find, but I'll save it to the next example maybe, okay? All right, maybe I'll save that next question to the next example, but anyway, what I'm thinking here. So this is kind of how one way we have a derivative and we apply it. Let's do something like this now. This is another relation. We have to get the derivative. Is that true? So what's the process again for this derivative? This is an ellipse. You guys know that? This is an equation of an ellipse. 4x squared plus 9y squared is 36. Differentiate the left side, which is 4x squared plus what? 9y squared. Differentiate your right side, which is what? 36. You guys okay with that? You're differentiating both sides of your equation. Y is a function of x again. So by properties on the left, I'm going to do this, okay? I'm going to use all the properties here. Using our operator notation. What do you guys get to do now with all this stuff? Differentiate x squared. Isn't that what? 2x. What's the derivative of y squared? 2y times y prime. Why? What did you guys use here? I'm going to keep doing that. We used what here? Chain what? Rule. Okay? Now be careful. Because you had constants to begin with, right? Notice this. And then what's the derivative of 36? Isn't that going to be 0? So we get 4 times 2x, which will be what? 8x. 9 times 2 will be 18y. Y prime equals what? 0. What do you guys do now? What's the next step in the process we wrote down yesterday? You solve for what? Good, solve for y prime. Okay. So translate, ladies and gentlemen. What do I mean by translate? Move this term to the other side of 0, or the equal sign. It's now going to be what? Negative. That's the same as subtracting 8x from both sides. All right, and then now divide both sides by what? By 18y, and we get cancellation. So y prime will be negative what? 8x over 18y. So you can simplify that. 2 goes into 8 4 times, and then 2 goes into 18 9 times. So ladies and gentlemen, here is your what? There is your derivative, ladies and gentlemen. There's your dy dx. Okay, you guys okay with that? Now, what if they ask us again? What is the location for the horizontal what? Tangents. They want horizontal tangents now. So automatically, what do? You set that first derivative equal to 0, and you solve for what? You solve for x. Is that right? Okay. So, what do you guys know? You're going to set that minus 4x, 9y equal to 0. You should be happy again. Why are you guys really happy? Your numerator is just 4x. So that means 4x equals 0. Another pre-algebra question. Pre-algebra. Divide both sides by 4. What is that? What's 0 divided by 4? X is what? 0. X is what number? 0. You go, what do you mean? That's not a location. That's a value of x. Let's go back to the curve here, right? Where is x 0, by the way? Is that where x is 0? I don't know. I don't think that's where x is 0. X is 0 is right here. Is that right? So this is where x is 0. This is where x is 0. Where's your y values when x is 0? I'm going to draw these horizontal tangents. I'm going to try to draw a straight line here. Because this time, what did they ask us? They asked us for the what? for the location this time. What does that mean, location? They want to know the x and y coordinate values. The point. We only have the x value. It's 0. We need the y value now. Okay, because what did they say? They want the what? The location. That's another way of saying what's the point. So we're going to have to now go back here, ladies and gentlemen, to the original curve here. Okay? What is the value of x? 0. Do you guys know what this does? That means 4 times 0 squared plus what? 9y squared is 36. Isn't this portion 0 again? So it means 9y squared is what? 36. Divide both sides by 9. What is y squared going to equal? 4. Is that true? Okay, now let's ask you guys, doing a little bit more algebra here. Does anybody know, how do you solve this? What do you use? Do you guys know what you use? Square root formula. Okay, so that means y will be plus or minus the square root of 4, which means y is plus or minus what? 2. Okay? So let's double check here. What is that saying? The second coordinate's the y coordinate. So there's two answers. One's positive, one is what? Negative. So this here is your what? Location. And take a look at the curve. Isn't that the address of 0, 2 and 0, negative 2? All right. So this is the location where you have what? Horizontal tangents. All right, ladies and gentlemen. Okay. Now, let me connect the dots here. You guys have all this information? Okay? What I didn't explain to you yet, and now I'm going back to do that. They'll say, what is the location of vertical what? Tangents. Do you guys know what vertical tangents are? Vertical tangent lines. Did we ever see that? We talked about differentiability. The answer is yes. There's vertical tangent lines. That's where the derivative what? Did not exist. Is that right? Okay. So go back over here. Here's some good news here. When you have a derivative like we have here, which is negative 4x over 9y. That's your derivative. How do I find where you have a vertical tangent? Well, now, ladies and gentlemen, you might say, isn't that derivative does not exist, or, okay? Well, let me remark about this. Now, you're going to look for this. I'm going to give you guys another fact about numbers here, right? When do you have a ratio being undefined? When the denominator is what? 0. Okay? So what you get to do now is set 9y equal to what? 0. And then, what's the good news again? You get to use some what? Pre-algebra again. So how do you guys solve for y? Divide 9 from both sides, and what does y equal? 0. Okay, that's a y value, ladies and gentlemen. It's not a point, but that's a y value where you have a what? Vertical tangent. It happens where y is 0. Now, if you go back to the curve here, this is different. When y is, where is y 0 now? Okay, go over here. Let's look at the points here. This is not the location, by the way. Let's do this all again now. Y is 0. We have what? We have vertical tangent. So, what we get to do now is plug in what? For y. We get to plug in 0 for y here. Because we're going to find the location, the point. 4x squared plus 9 times 0 squared. That's what y is now, is 36. So the good news is this portion is 0. And you have 4x squared is what? 36. Divide both sides now by what? 4. You get now x squared equals what? 9. What does that mean then? The square root formula, plus or minus square root of 9, and that means now x is plus or minus what? 3. Again, 2 solutions. Now, when they want a location, they're talking a what? X coordinate, y coordinate. So the locations are going to be where x is positive 3, y is 0, x is negative 3, y is 0, and I'm going to color this purple. Because those locations, ladies and gentlemen, are here. That the tangent line, this is the address here, 3, 0 and negative 3, 0. So your tangent line, again, I can draw a straight line, kind of, has, these are vertical tangent lines. So you're really looking at something that's really meaningful in terms of location. You did some algebra, pre-algebra, and intermediate algebra, square root formula. Some cases, beginning algebra. So you found locations for vertical and what? Horizontal tangents. And, you know, it's really good to see that in terms of these things called relations. It's another setting where you see these kind of ideas. So anyway, this is why you care about finding a what? A derivative. Okay. And let's do something here. I think I want to come back to something. Oh, yeah, you got the limicon. You got these kind of curves. Okay, and trig. Hey, let's kind of look at this. This curve here. Or let's double check. Let me do something here. Let me check your book really quick. 0, 1/2, the cardioid. Let's go back to the cardioid. Okay. Okay. So, ladies and gentlemen, here's what I'm going to ask you guys now here, okay? Yes, we're going to get the derivative here. But what kind of questions do they ask here? They might say this. They might say, determine the what now? The equation of the line. Tangent to the what? Curve at the location 0, 1/2. Okay? So notice this. This is just like everything we did before, but now I have to find the equation of the line, again, and tangent to the curve. So what did that mean? Do you guys remember? This is not finding horizontal tangents. It's not finding vertical tangents. It's still finding a derivative, but what's the format that you have to use here? It's equation of the line. That's what? Tangent to the curve. Well, that's called our what? tangent at what point? This is the point they're giving you. Okay, x is 0, y is 1/2. So you have a tangent to the curve there. They want that equation. That's called the equation of the tangent line. So what's the format? Do you guys remember? You want to write it down this way, right? This is y minus what? y1 is m tangent times what? X minus x1. So it goes back again to beginning algebra. Did they give you guys a point? Yeah, they gave an x and y coordinate. They gave us an x1 and a y1. In this case, x1 is 0, and y1 is what? 1/2. So we have y minus 1/2 is m tangent x minus 0. And what is x minus 0? Isn't that just x? Okay. And I'll do a little bit more algebra, okay? It's m tangent x plus what? 1/2. If we translate or add 1/2 to both sides, is that right? It's now in slope-intercept form, but isn't it true you need m tangent? How do we get the slope of the tangent line? Okay, do you remember this? This is all the details we went over. So the slope of the tangent line is going to be, well, what's that definition? dy dx evaluated when x equals what? 0. In fact, because we have a relation, it's evaluated when x is 0 and y is what? 1/2. You're going to see my point here. So it goes back to finding a what again? A derivative. That's what you have to find. So this is putting together all the details that we've talked about and the justification for why we find derivatives. All that little details jallying together. Okay, so you said, but isn't this about implicit differentiation? It is. So how do we find a derivative, ladies and gentlemen, for a relation? Isn't that a relation again? You're going to have to use what? What do you use? Implicit differentiation again. Okay, so what was implicit differentiation? Right? You guys remember? You're going to have to do what? Not yet. We have to do the derivative of the left and the right side, right? So on the left side, you got what? What's on the left side? X squared plus what? Y squared. Okay. And then on the right side, you say, what's on the right side? Well, 2x squared plus 2y squared minus x. And that's raised to the second power. So this is our implicit what? Differentiation. All right, so double check we got the right curve. We do. And does anybody remember this from trig, by the way? Anybody here take the trig? Because I remember when I teach trig on the final exam, what I do is I give people the equation of the cardioid in polar form. And then I ask those students to write it in rectangular form. So they convert the polar to what? Rectangular. What do you think I took this from a trig. Took that function from a trig final. Okay, so that goes back to the trig course. Okay. All right, now using this implicit, differentiate both sides, right? So you have to differentiate by properties here. Differentiate x squared, and you differentiate the what? Y squared. And then that's going to equal what? going to do this. Let me do it this way. Okay, so now we take the derivative. Okay, by properties, what's the derivative of x squared? Do you guys know? We must have seen it 3 or 4 times. Okay, what do you guys have to do here now? What is this going to be? Chain rule. Okay, what's that derivative going to be? Isn't that 2y prime? Is that right? All right. Now, on the other side, guess what? On this side, you're also going to use what again? We're going to have to use what again here? Chain rule as well. So, what am I talking about? Right? If you have a function to a power, aren't you actually using the power rule for chain rule? Right? Aren't you using this portion here for chain rule? All right, let's see what this is. So what do you have here? Let's try that out. That's going to be 2 what? 2x squared plus 2y squared minus x times, this is the chain, 2x squared plus what? 2y squared minus x. This is the chain portion. Okay, so far so good? So the real work now, I'm going to just kind of put a highlighter here, is right in here. So you go, oh, what work's that going to be? Well, by properties of derivatives again, 2 d dx of x squared plus 2 d dx of your what? Y squared minus d dx of x. So this portion gives me again 2x. This portion here, what is this? Do you guys know? I'm going to put CR. What's that going to be? Thank you. 2y what? Y prime. And then what is this? Isn't that 1? Okay. Now we're going to try to put this together here, okay? So I'm going to go back and highlight this so you guys can see. This is 2x, 2y prime. That's on the left side. On the right side, let's not forget all these details. Okay? So I'm highlighting the left side and the right side. So let's see what's on the left. 2x plus 2y, y prime. So let's write that down. There's what you see on the left. Now on the right, you have what? 2 times 2x squared plus 2y squared minus x. Now this is going to be times, okay, so double check to see if we left anything off, times 2 times 2x is what? 4x plus 4y, y prime, minus 1 here. Parentheses. We're out of space. Maybe I can fix it. I can squeeze it in. Let me double check. Okay, 2y squared, yep, minus squared. Okay. All right, maybe I can. Okay. Now, yes, ladies and gentlemen, there is a way to use algebra to solve for y prime. Okay, so generally speaking, I'm going to put a note here. Okay, generally speaking, note, yes, for implicit, you want to solve for y prime. Okay, however, what's nice about this question? Do you guys know what's nice? You know what you can do? Yeah. Why can I plug in x is 0 and y is 1/2 now? See, because they're asking yes to find the derivative at a location. So what I can do now is wherever there's an x, plug in your point, right? The point here, remember, what's the whole idea? Find the derivative at that location. So x is 0, x is 0, x is 0, x is 0. Y is what? 1/2. 1/2. 1/2. Okay, you guys okay with that? That's going to make your life a lot easier because now you get on the left side 1/2. You say, why is that one 1/2? Well, what's 2 times 1/2? Isn't that 1?
Yeah.
So that's just y prime there. Okay. And now that'll be 2 times. This portion is 0. Isn't that 2? What is that? 2 times what? Is that 1/4, I think? Yes. Parentheses. 4 times 1/2. Isn't that 2 y prime, I think? Oh, I forgot the 1. Okay. Double check. Now, this portion is going to be what here? 1. Is that true? So I get y prime is going to be now 2y prime minus 1. So double check to see if my arithmetic's okay, because sometimes talking and writing is not as easy as you guys think it is. And again, now you got a little bit of algebra to do, right? Because you're supposed to solve for what? What's y prime at that point? Double check. What's that going to be? If I translate here, right? And that could be negative y prime is what? Negative 1, or we say y prime is what number? That's going to be what number here? Is that 1? Double check. So what did you guys just find here? That this is really the number what? 1. And final answer, we go back and this is 1 here. Copy that. We get y equals x plus what? 1/2. And what do we call this line again? Tangent line. Okay, that was the cardioid. Is that right? Now let's see, just to kind of double check here. I want to demonstrate to you guys here. Did I still have that cardioid in Desmos? There's a cardioid. So I'm going to put this equation, y equals x plus, well, 0.5 is 1/2. Okay? Now, sure enough, what do you guys see? Isn't that kissing the curve at the point 0, 1/2? Okay, there's the tangent line we're looking for, ladies and gentlemen. So those are all the details. All right, now let's recall. I want you guys to note this as well. What if they ask you for, what is this? And you guys can't see that, but okay. What if they ask us for the normal line?
Change the sign.
How do I find a line that's perpendicular at that location? That's the normal line, right? Do you guys remember? Didn't we talk about that? What do you guys know? You guys remember, these lines have to be what? Perpendicular, orthogonal to one another. So what if they want not the tangent line, but they want the normal line to the curve? So they change it now. So now I have to have a different slope here. They don't want tangent line. What do they want here? The slope here for the what? Normal line. So does anybody remember? You still have to get the derivative at that point. But what's the difference now?
Opposite reciprocal.
Yeah, so let's kind of write this down here. Let's remember here. If the slope of the what? Tangent line is positive 1, then the slope of the normal line is opposite and reciprocal, which will make it just simply what? Negative 1. So this is going to be here now what? Negative 1. So the equation here is negative 1x, which is negative x, plus 1/2. So I'm going to just kind of leave it like this for you. And maybe we should see that in Desmos and color it purple. Let's make that purple here, okay? And I am going to actually just put it as a negative there for you guys. Let's go back. Y equals negative x plus point what? 5, and we want that to be purple. Let's get rid of that. So let's take a quick look. You know, maybe we can scroll out, I guess. I don't know. It looks better. But ladies and gentlemen, does that kind of look like what we're talking about? I think it does. Is that true? All right, pretty good. All right, nice. Let's go back. Now, this is another curve that I give in a trig class, and I say, hey, can you guys, here's the polar version, translate that to the rectangular version, and there you go. And then, by the way, ladies and gentlemen, I'm gonna say this to you guys. You see these polar curves? This is from Math 241. This is a cardioid, the heart, right? And then here, this is going to be a limicon. This is another polar curve. In Calculus 2, the good news is you get to do this all over again, but with polar curves, meaning R is f of theta and polar relations. You know, so you get to do them both in two settings. One is rectangular and one is polar. The polar version in some ways is easier, but the calculus is a little bit more sophisticated, believe it or not. But, I mean, you could look at a lot of curves here, ladies and gentlemen, in theory that are pretty what? Interesting. Like, what about this curve, the asteroid? You know, like even in our book. Negative 3 squared root of 3, 1. In our book, they'll give you a point. Sometimes we call that P. And they're going to want the what? Equation of the line tangent to the what? The curve. At that point P. Sometimes they just call it P. This is that location P. Something like that. We'll see. So again, what do you guys know? This has to be what again? Right? I'll put it here. Y minus y1 is m what? Tangent x minus what? x1. Here's your one and only point here, right? Here's the one point, x coordinate, y coordinate. So we have 1 here and minus 3, what? Square root of 3. So you have that y minus 1 is m tangent minus the minus will make that a what? Plus now. And we're not done with the equation, but we need what? M tangent, the slope of the tangent line. This is where you have to use your what? Implicit differentiation. So to find that, implicit differentiation, so differentiate both sides with respect to x. So we have x to the what? 2/3, y to the 2/3, and that derivative is supposed to equal, what's the number? 4. So now just use your properties. Okay. Ah, what happened? I didn't put space there. It's okay. Okay, so remember, the only thing you have to be concerned with is here. This is going to be what again? Chain rule. This is going to be 0. What is this? Do you guys know by power rule? 2/3 x to the what? 2/3 minus 1. This one's going to be again 2/3 y to the what? 2/3 minus 1 by chain rule times y prime. Okay, you guys okay with that? So what is 1 again? Isn't that 3/3? So you say, is this 2/3 x to the what? Negative 1/3 plus 2/3 y to the negative 1/3 times y prime equals what? 0. So double check. Okay, so just doing a little bit of algebra here. That's 2/3. Well, let's do it this way. Let's remember here, we're going to have to solve for what? Step 2, solve for y prime. So you can translate or subtract that term from both sides, and you get now what? 2/3 y to the minus 1/3 becomes negative 2/3, and I think I need a y prime. Let's double check. Okay. X to the negative 1/3. And don't your 2/3 cancel? So you got y prime over the cube root of y, which is 1 over, really negative 1 over the cube root of what? X. So y prime will be now the cube root of y over the cube root of x. There's a negative sign there. And if you're really awake by properties, that's just the cube root of what? Y over x. Okay, so here's your derivative. We can do a lot of interesting things with this. But what do they want to know? It's at what point? We need m tangent, right? At what location? This is my x-coordinate, negative 3 cube root of 3, comma 1. So m tangent. Evaluated at what? Negative 3 cube root of 3, comma 1. Is that true? Okay. So m tangent was negative cube root of what? What is y? 1? And what is x? Negative 3 cube root of 3. Is that true? Anyway, m tangent. Okay, what's that going to be? I should have left it the way it was. Oh, did I make a mistake? No. I think we're good. Okay. 1, here's what? Negative 3, what? Cube root of 3? Let's double check. Just going to check the algebra here. Okay. Okay. If I left it alone on top, isn't that going to be 1? And then that's the cube root of what? Negative 3 cube root of 3, or square root of 3. Okay. So let's bring down this here. And I think your book is going to probably leave it that way. Okay, so you might say, looking back at the book, y minus 1, negative what? 1 over cube root of negative 3 square root of 3 x plus 3 square root of 3. So your book will leave it like this, I guess. And then that's the asteroid, I guess. Okay, so let's go back here and take a look. I didn't even do the lemniscate, which is fine. Let's see the derivative here. Happens when x is 0. Okay, now I want to share with you guys something that I did yesterday, which was interesting. So here's our solution. Let me go to Desmos really quick here. Okay, I don't think I have it on this computer, but I'm going to share with you guys another curve. 4 cosine x sine x equals 1. Okay. So take a look at this, okay? What I entered here is another relation, which is 4 cosine x sine y equals 1. This is kind of one in your book where they want you to do implicit differentiation. They just want you to take the derivative. Find dy dx. But my point to you is, isn't that amazing? Did you even know that such curves exist? So as you look at some of these curves on your homework, right? You know, I'm looking at 5, this is 3.7. As you look at some of those curves, you might want to go over to Desmos and punch some of those in to take a look at what they really are. Because there's a lot more of those curves than you realize. In calculus, or I should say not in calculus, in pre-calculus and algebra, we only study just a small amount of what? Functions and relations. Just a small amount. And here, like 5 to 13, the odds, you might want to punch some of those in Desmos and then take a look at what they're talking about. Not that they're going to ask you to graph this. They're not. They may not even ask you to find the equation of the line tangent of the curve at a point. They're just having you find the derivative there for those dy dx by using implicit differentiation. Now, I can do that right now, but we're out of time. I would love to do that, but, you know, try that out. Let's see how it goes. Maybe we'll try this one tomorrow just so you guys can see. Okay, you guys okay with that? So try those out and take care. And I hope you guys took some review of the what? Of the algebra. Did you guys see the algebra? And all those ideas we talked about. Okay, we'll see you guys tomorrow. Take care. Another look, if you guys remember, you have a relation here. And in Desmos, I actually graphed that for you guys yesterday. And let's make sure our audio is on here. Oh, yeah, audio is wrong. Okay. And if you look at that, you might say, oh, Mr. Judge, I have never seen, I don't even think they're squares. They are, wow, don't know what they are. There's a lot more things that you have not seen than what you have seen. And yes, you can still, you know, take derivatives and work with the same ideas, you know. But I don't know. I'm just looking at that. I don't know. How do you guys feel about that curve?
What's the name of the curve?
I don't even think it has a name.
Oh, so it's just like passing.
There are so many random curves you can write down that they haven't really all been named. This is one. I just took this out of your book.
I'm naming this Spunkle.
I'm naming it, you know, I took it out of your book. So what I wanted to do, you know, with you guys is just simply show you how to do what? How to take a derivative implicitly. Because you have some in your book that way. Is that true?
Yeah.
So what's the process, ladies and gentlemen? You differentiate what? Both sides with respect to what? X. Is that true? And when you do, you may notice something here. What do you guys notice? Yeah, we can do product rule here. Is that true? I mean, we can do actually a few things. I can say to you, hey, should we pull out our constant? Well, we don't have to, but okay. So you guys can see here, yeah, we're going to end up using what? Product rule. Okay. So notice this. If you never learn product rule, right, remember you pull out the what? Second function, differentiate the first. Okay? And I'm going to differentiate this now. Derivative of a constant is 0, okay? So there you go. You guys okay with that?
Yep.
Now, I'm going to do the easy one first. What's the derivative of cosine? Negative sine. Is that true?
Yep.
And then, to remind you guys over here, this is where you're going to need to use what again? The derivative here is with respect to x, and you got sine of y. remember what do we assume about y? Y is a function of x. So you're going to have to use chain what? Rule. For what function? For sine. So you might say, I don't know what that is. Well, if you have sine of, your book uses u, I won't do the triangle. Derivative of sine is what? It's cosine u times u prime. Is that right? Which is really, if you said, what is u prime? Well, it's du dx. It's with respect to the x variable. So this portion here now, by chain rule, you say, is that going to give me cosine y times y prime by chain rule? And the answer is what? Yes. So for cosine x, cosine y times y prime there. Now be careful. I'm just going through this here so you guys can see every detail. For cosine x is there. You got the sine y and just got the minus sine y. So that's actually minus sine y squared, right? Okay. And of course that equals 0. So what do you guys do now with the constant here? Do you guys know? Well, we could do another thing. Let's go back here. Remember, we have to solve for y prime. Is that true? Because after you find the what? The derivative, differentiate both sides with respect to x, you got to solve for y prime. So this is what I'm saying. If you guys know, can I divide both sides now by that 4? And what that actually means is cosine x, cosine y times y prime minus sine squared what? Y. What's 0 divided by 4? Is 0. And this is a lot easier to solve for what? Y prime. Yep.
Doesn't sine y like less? Where'd you get the sine squared?
I think did I make a mistake?
Yeah.
I did make a mistake. I apologize. I made a mistake. I should have went to go get that coffee. That's sine y sine x. Okay. Sine y sine x. Okay. Thank you. Okay, let's do that here. Ah. So this would be minus sine y sine x. Okay, you are correct. It looks like I was eager to do the other derivative first. Okay. Now, here's what I want to remark here. I mean, you guys can add. I like to translate. You guys are calculus students, so this translation for algebra, if you guys know, you're always able to move what? A term to the other side, just change the sign. And maybe you want, I'm going to do this as well. Maybe you want to be systemic about putting sine x, sine y, because, you know, as we proceed to solve for y prime, we're going to divide this by both sides, cosine x, cosine y. Okay, and you cancel, and you get what? Y prime going to be sine x, sine y, cosine x, cosine y, and then I'm going to say to you guys, sine over cosine is tangent. Yeah, tangent x, tangent y. So, ladies and gentlemen, here you go.
Is that a book problem?
Yeah, it's from your book.
Yeah, it seems kind of familiar.
That's a book problem. So I wanted to try that, ladies and gentlemen.
I have another question. Do we have to like convert it into tangent?
I think in this case, I mean, I wouldn't mark it wrong if you didn't, but I think it should be simplified when you can. You know, I'm not saying you want to go through every identity you know, but sine over cosine
It's pretty obvious.
is a pretty common thing to see. So sine over cosine, and it's different variables. But notice there's your derivative. And it's a derivative, you know, I'm not going to try to create another example. I'm not going to say, hey, because obviously, you know, your sines and cosines and tangents are periodic functions. Which makes sense that this behavior you guys see here is very much periodic. These curves, again, some of these have no names, you know, because you can't name every curve you see, and you know that's, you know, you could. There's infinitely many curves, so there's no way to name them all. But again, I see this and I think, wow, that's pretty interesting for myself. You imagine maybe that's the cure for COVID or something, and we don't even know. That's why you need math and science, ladies and gentlemen. There's so many things that we haven't even yet discovered how to apply. And that's the way it is, you know, in the world of math and science. So there's a lot of math out there that, you know, we haven't applied yet. And as we move forward with technology and science, then the math is already there in terms of the framework, really. Anyway. Okay, now the title of today's lecture is really higher order derivatives, right? And you might say, what's a higher order derivative? I mean, they can even give you a higher order derivative here. So higher order derivative